So now I want to talk about quotient spaces. So I will introduce a relation in my set X given Y a linear subspace. So I have my set X, and I consider Y a linear subspace of the set X, and I'm introducing a relation between elements of X. So the definition is that X it's related to Y if X minus Y belongs to the set Y. Okay? And what I claim is that this relation it's an equivalence relation. Right, so I have to prove that X it's always related to X, and this is clear because, well, X minus X it's equal to 0, which is an element of Y, because Y it's a linear subspace. Right? And maybe I haven't proven that, but that's clear because 0 it's always an element of a linear subspace because, well, if it's, I'm always assuming that Y it's non-empty, so take an element of Y. Since Y it's a linear subspace, this means that minus 1 times Y belongs to Y, but we have seen that this is minus 1 minus Y. And also, because Y it's a linear subspace, we know that Y plus minus Y belongs to Y, but Y plus minus Y it's 0. So this proves that 0 it's an element of Y. So I've just shown that if Y it's a linear subspace, then 0 it's an element of Y, which is what I am using here to show that X it's related to X. So now the second property of an equivalence relation is that if X it's related to Y, then Y it's related to X. But this is also clear because if X is related to Y, this means that X minus Y belongs to Y. And if X minus Y belongs to Y, since Y it's a linear subspace, minus 1 times X minus Y belongs to Y. And minus 1 times X minus Y, it's minus X plus Y. So this proves that Y minus X belongs to Y, and therefore that Y it's related to X, which is what I wanted to show. And finally, we have to show that if X it's related to Y, and if Y it's related to Z, then X it's related to Z. So let's prove that. X it's related to Y. This means that X minus Y belongs to Y. Y related to Z means that Y minus Z belongs to Y. And if these two elements belong to Y, the sum belongs to Y because Y it's a linear subspace. So this means that X minus Y plus Y minus Z belongs to Y. And by since we know that the sum is associative, we can have this is equal to X minus Y plus Y minus Z. So this is X minus Z. So X minus Z belongs to Y, and this means that X is related to Z as we wanted to prove. So this relation defined by this condition is an equivalence relation. Now, if I have an element X in X, I will represent by this symbol all the elements y in X which are related to X. And I will represent by X quotient Y the space of all these families. So this is called the quotient space of X modulo Y. So this is X modulo Y, the quotient space of X modulo Y. And this is the set of all equivalent classes X. So it's a set formed by subsets of X, right? Each element of X modulo Y is actually a subset of X. It's the subset of all points of all elements Y of X which are equivalent to Y. And I want to define a sum and a multiplication which turn this set a linear space. So I want to define the sum of two elements of this quotient space, and I want to define the multiplication by a scalar and of a scalar with an element of this space. So how do I define this sum? Well, that's very easy. Take an element of this set. Say I'm taking x1, an element of this set. Take an element of this set, y1. So let me write this as x1 belongs to this family, to this set. y1 belongs to this set. Mind that these are subsets of X. So I'm taking one element and another element of this set. I'm considering the sum. And now I take the equivalent class of this sum, and I will define the sum of these two elements as the equivalent class of this sum. Of course, I need to show that this sum is well defined, so that this set will be equal to the set x2 plus y2 if I consider another representative x2 of this set and another representative y2 of this set. So what I have to show is that these two sets are equal if I take x1 and x2 equivalent to x and y1 and y2 equivalent to y. So saying that x1 its equivalent belongs to this set means that x1 is equivalent to x. This means that x1 minus x belongs to y, and that x2 minus x belongs to y. So that if I take the difference, I get that x2 minus x1 belongs to y. And by the same reasons, that y2 minus y1 belong to y. And what I want to show is that these equivalent classes, it's equal to that one. So let me take an element z in this equivalent class, and I have to show that it belongs to that one. Well, and this same argument is symmetric, so it will also, so that will prove that this set is contained in that one, and by symmetry, the same argument will apply to show that this set is contained in that one. So I'm assuming that z belongs to x1 plus y1. This means that, what does it mean? That this means that z is equivalent to x1 plus y1, which means that z minus x1 plus y1 belongs to y. But why it's a linear space? So I can now write this as x1 plus y1 plus or better, plus z, I'm writing this element at z minus x2 plus y2 plus x2 plus y2 minus x1 plus y1. So I did nothing, I just added and subtracted x2 plus y2. But now I know that this element belongs to y, right? Because, I'm sorry, I want to prove that this element belongs to y. What I know is that, sorry, z is an element of this set. This means that this z minus x1 plus y1 belongs to y. Now I'm adding x2 plus y2 and subtracting x2 plus y2, so this is still an element of y. But now I know that x2 minus x1 belongs to y. So this means that if I take this element so let me not write it again. So I'm just rewriting this element, which is an element of y. And I know that x2 minus x1, it's an element of y. So if I subtract x2 minus x1, this is still an element of y. And if I subtract y2 minus y1, this is still an element of y, because y is a linear subspace. Now what I know is that this element is an element of y, but if I look at this element, I see that x2 minus x1 minus x2 minus x1 will cancel. So this x2 minus x1 will cancel with this one. Then I have plus y2 minus y1, which will cancel with the minus. And what will remain is that z minus x2 plus y2, it's an element of y, which shows that z, it's equivalent to x2 plus y2, which means that z belongs to this set, the equivalence class of x2 plus y2. So maybe let me repeat, because I don't know if I have been very clear. I want to show that this set is contained on that one. So I take an element of this set, and I want to show that it belongs to that set. If z is an element of this set, this means that z minus x1 plus y1, it's an element of y. Now, let me add and subtract x2 plus y2. And I still have an element of y. And now, let's further. So this is an element of y. Now I know that x2 minus x1, it's an element of y, so I can subtract this element and still have an element of y. I can also subtract this element and still have an element of y. So this element which appears here minus these two elements, it's still in y. Now let's see that x2 minus x1 appears here and it's subtracted, so it goes away. y2 minus y1 appears here and over there, so they also cancel. And what remains is that this subtraction is actually equal to z minus x2 plus y2, and we know that this is an element of y. So this means that z is equivalent to x2 plus y2. In other words, that z belongs to the equivalence class of x2 plus y2, which means that z is an element of this set. So this proves that this set is contained on that one. With the same argument, we can prove the reversed inclusion to show that these two sets are equal, and therefore that this sum does not depend on the representative we take for both sets. So this sum is well defined. Also, you can show in the same way that this multiplication is well defined by exactly the same arguments, and therefore we can transform, we can introduce in this set the quotient set of x modulo y a sum and a multiplication by scalar, which transform this quotient space into a linear space. So now let me introduce linear maps. So let's say that we have now two linear spaces x and x star over the same field K. And I have a map T from x to x star, which means that T sends any point x or in x to a point in x star. And I will say that this map is linear if it satisfies two properties. First, that T of x plus y is equal to T of x plus T of y. And if T of alpha x, it's equal to alpha T of x, and this for all x, y in the set X and all alpha in the scalar in the field K. Note that I need these two spaces to be defined on the same field, so I need the multiplication, the field which appears in the multiplication to be the same, because alpha x, we have alpha x here, and alpha tx, so now tx is an element of x star, and therefore we need the multiplication to be defined on the same field. So this is the definition of a linear map. And I would say that x and x star are isomorph if there exists a linear map T from x to x star, which is a bijection. Right, so the two space x and x star will be said to be isomorph if there exists a linear map between x and x star, which is a bijection. Now, I fix a linear map from x to x star, so this will be a linear map. And I have two claims. The first one is that if I take y, a subset of x, which is a linear subspace, and I represent by t of y all the points t of x such that x is an element of y, then what I claim is that t of y it's a linear subspace. So let's prove that. So let's consider alpha in K, z1 and z2 in t of y, and I have to show that alpha z1 plus z2 belongs to t of y. Well, if z1 and z2 belongs to t of y, there exists x1 and x2, which belong to y, and such that t of x1 is equal to z1, and t of x2 it's equal to z2. Since y it's a linear subspace, this means that alpha x1 plus x2 belongs to y, because y it's a linear subspace, and x1 and x2 are in y, and alpha it's a scalar. But this implies that t of alpha x1 plus x2 belongs to T of y, by definition of T of y, because T of y is the sets all points which are T of an element of y. But which point is this? So let's use the linearity of T to say that T alpha x1 plus x2, it's equal, so I'm writing this identity here. Well, let's use linearity. I erased already the properties of linear maps, but I hope you recall them. So that this is equal to T alpha x1 plus T of x2 by linearity, and this is equal to alpha Tx1 plus T of x2, again by linearity. And what is T of x1? This is z1, and Tx2 is z2. So this is alpha z1 plus z2. So we just proved that alpha z1 plus z2, which is equal to T of this element, belongs to T of y. And this is exactly what we wanted to prove. So this shows that if you take a linear map T and a linear subspace y, then the image of y by T, it's also a linear subspace. Now, let's consider a second property. So let's take y star, a linear subspace of x star. And let's consider the inverse image of y star, which I'm representing by t minus 1 of y star. So this is by definition the set of all points x in X, such that t of x belongs to y star. And what I claim is that since y star it's a linear subspace and t it's a linear map, then the inverse image of y star is a linear subspace. So let's prove that. So to prove that, I need to consider 2 points, z1, z2 in the inverse image, and alpha a scalar, and I want to show that alpha z1 plus z2 belongs to the inverse image. Right? Okay, but since z1 belongs to the inverse image, this means that t of z1 belongs to y star. This is exactly the definition of the inverse image. Right? Since z1 belongs to this set, this means that t of z1 belongs to y star. And the same thing for z2, so I know that t of z2 belongs to y star, and therefore, by linearity of t, t alpha z1 plus z2, which we have seen by linearity, it's equal to alpha t z1 plus t z2. Well, tz1 and tz2 belongs to y star. Alpha, it's a scalar. Since y, it's a linear, y star, it's a linear subspace, this means that this set belongs to y star. And therefore, the image of alpha z1 plus z2 by t belongs to y star, which means that alpha z1 plus z2 belongs to t minus 1 y star. And this is exactly what we wanted to prove. So this shows that indeed the inverse image of y star, it's a linear subspace. So what did we prove? If you take T a linear map, y star a linear subspace, then the inverse image of y star, it's also a linear subspace. So now let's talk about convex sets. So definition, a subset K of X is said to be convex if for all, and here now I'm taking K to be the real sets. So whenever speaking about convex sets, it's understood that the field is actually the set of real numbers. So let's go back. I'll say that a subset K of X is convex if for any x, y in K, and for any theta in, or maybe alpha in 0, 1, alpha x plus 1 minus alpha y belongs to K. Right, so this is the definition. Examples of convex sets are, well, in the plane, the disk, a triangle. Right, you see that if you take any point, you take any combination of these 2 points, it will belong to the disk. The same thing for a triangle or square. But of course, if you take a star-shaped set, this one is not convex, because if you take 2 points on these 2 points, and you take combination of these 2 points, some of them won't belong to the set. So these are very simple examples of convex or non-convex sets. But what I claim is that if K is convex, and if I take x1, xn in K, and alpha 1, alpha n in 0, 1, such that the sum is equal to 1, then any convex combination of these points by this vector, which means that alpha j xj from 1 up to n, that this also belongs to K. So this is a claim, and a terminology. This will be called a convex combination of elements of K. Right, so a convex combination of an element, it's like a linear combination, with the difference that all the alpha j's are non-negative and they sum up to 1. The sum is equal to 1. So these are what we call the convex combination of elements of K. And what I'm claiming is that if K is a convex set, any convex combination of elements of this convex set belongs to the convex set. And so how you prove that? You prove that by induction. So maybe let me try to prove that here. So the proof is by induction. For n equal to 2, this is just the definition, right? Because for n equal to 2, alpha 1 plus alpha 2, it's 1, which means that alpha 2 is 1 minus alpha 1. So we can write in this way the convex combination, and by definition, this is an element of K. So assume that this has been proven up to n, and we want to consider a convex combination of n plus 1 elements. Right, so I can write this as alpha 1 x1 plus alpha j, xj, j from 2 to n plus 1. I want to divide it by and multiply by 1 minus alpha 1. Well, to divide, I need to guarantee that alpha 1 is not equal to 1. So let's divide it in two cases. The case in which alpha 1 is 1, and the case in which alpha 1 is less than 1. If alpha 1 is 1, this means that this set is actually equal to x1, but x1 is an element of k, by definition. So I can assume, so if alpha 1 is equal to 1, then it's obvious that this is an element of k. So now let's consider the case in which alpha 1 is different from 1. If alpha 1 is different from 1, I can divide it, alpha j by 1 minus alpha 1 and multiply it. Now I claim that this is an element of k, and this follows from my induction assumption because, well, if I sum alpha j from 2 to n plus 1, I get 1 minus alpha 1. So the sum of these expressions, it's equal to 1. Since each xj belongs to k, by the induction assumption, this is an element of k. And if this is an element of k, I have here a convex combination of two elements of k, which belongs to k by definition of convexity. So by induction, this proves that any convex combination of elements of k belongs to k as I claimed. So let me prove some properties of convex sets. The first one is that if Y it's a linear subspace, then Y is convex. And this is very easy to prove. Take x1, x2 elements of Y, theta in, or maybe alpha in 0, 1. And we want to show that alpha x1 plus 1 minus alpha x2 belongs to Y. But since Y is linear, alpha x1 belongs to Y, 1 minus alpha times x2 belongs to Y, and the sum belongs to Y. So this is an element of Y, and this proves that Y is convex. So the first property is very simple. Let me prove a second property. Let's take Y1 and Y2, two convex subsets. Of X. And what I claim is that the sum, it's also convex. So remember, the sum, the elements of the sum are elements which can be written as an element of Y1 plus an element of Y2. So let me take Z1 and Z2 elements of Y1 plus Y2 and alpha between 0 and 1. And I want to show that alpha Z1 plus 1 minus alpha Z2, it's an element of Y1 plus Y2. Right? So let's prove that. I know that Z1, it's an element of Y1 plus Y2. So Z1 can be written as X1 plus Y1, where X1 it's an element of Y1, and Y1 it's an element of Y2. All right? Now, the same thing for Z2. Z2 can be written as X2 plus Y2, where X2 it's an element of 1, Y2 it's an element of Y2. Now I want to consider alpha Z1 plus 1 minus alpha Z2. But Z1, it's X1 plus Y1. and Z2, it's x2 plus y2. So now I can rewrite this as alpha x1 plus 1 minus alpha x2. So this is the first two elements, and then plus alpha y1 plus 1 minus alpha y2. And these are the second elements. Now, x1 belongs to y1, and x2 also belongs to y1. y1, it's a convex subset. Therefore, this element, which is a convex combination of x1 and x2, belongs to y1. In the same way, y1 and y2 belong to y2, which is a convex set. This means that alpha y1 plus 1 minus alpha y2 belongs to y2. And therefore, the sum of this element with that element is an element of y1 plus y2. So this proves that alpha z1 plus 1 minus alpha z2 belongs to y1 plus y2, which is what we wanted to prove. So we just have shown that if you have two convex subsets of X, then the sum of this set is also convex. Now, third property is that if I have a family k theta, theta in some index set I of convex sets, so I'm assuming that I have a family k theta, where for each theta in I, k theta, it's a convex set. Then what I claim is that k, which is defined as the intersection of k theta, it's convex. This is, again, very easy to prove. Take x and y in k, and alpha in 0, 1. We have to show that alpha x plus 1 minus alpha y belongs to k. So fix theta in I. Since x and y belongs to k, and k is the intersection, they belongs to k theta. But since k theta is convex, this implies that alpha x plus 1 minus alpha y belongs to k theta. Because alpha is between 0 and 1. So this is a convex combination. And since this is true for any theta, this implies that alpha x plus 1 minus alpha y belongs to k, which proves that k, the intersection of k theta, whatever intersection we take of convex set, is still a convex set. Now, another property, I think it's the fourth one, is as follows. Consider family k theta of convex sets for theta in some set I, and assume that this family is totally ordered. Remember, this means that if I take theta 1 and theta 2, either k theta 1 is contained in k theta 2, or k theta 2 it's contained in k theta 1. So I'm considering a family of convex sets indexed by some set I. I don't impose any condition on I. I insist it can be uncountable. But now I'm assuming also that this family is totally ordered. And what I claim is that the union of k theta is also convex. So to prove that, I have to consider alpha in 0, 1, xy in k, and we need to show that alpha x plus 1 minus alpha y belongs to k. Well, since x and y belongs to k, this means that there exist theta 1 and theta 2 such that x belongs to k theta 1 and y belongs to k theta 2 because x belongs to the union, so it has to belong to one of them, and the same thing for y. So we can assume without loss of generality that k theta 1 is included in k theta 2. This means that both x and y belong to k theta 2. Since k theta 2 is a convex set, this means that alpha x plus 1 minus alpha y belongs to k theta 2. But k theta 2, it's contained in k because k is the union. So we proved that alpha x plus 1 minus alpha y belongs to k, which is exactly what we wanted to prove. Now let's assume that we have a linear map. And, okay, so the fifth property states that if you have K a convex set, then T of K it's convex. So this means that linear maps send convex sets to convex sets. So again, what we need to show is that if you take Z1 and Z2 in T of K and alpha between 0 and 1, then we want to show that alpha Z1 plus 1 minus alpha Z2 belongs to T of K. Well, but since Z1 belongs to T of K, this means that there exists, remember T of K, it's the image of K by T, so this means that there exists x1 in K such that T of x1 it's equal to Z1. And also, since Z2 belongs to T of K, there exists the x2 in K such that T of x2 it's equal to Z2. Well, but since K is a convex set and alpha is between 0 and 1, we know that alpha x1 plus 1 minus alpha x2 belongs to K. Since this element belongs to K, this means that its image belongs to T of K. But by linearity, the image of this point, it's alpha Tx1 plus 1 minus alpha Tx2. And Tx1 is Z1, Tx2 is Z2, which means that alpha Z1 plus 1 minus alpha Z2 belongs to T of K, which is what we wanted to prove. And so this proves our claim. So the last property is similar, but now, so I still have a linear map from X to Y, but now I am assuming that I have a set K, which is a subset of Y, which is convex. And what I claim is that its inverse image by T, it's convex. So to prove that the inverse image is convex, I have to take 2 points, x1, x2 in the inverse image of K, alpha in 0, 1. And I want to show that alpha x1 plus 1 minus alpha x2 belongs to the inverse image of K. So this is what I want to prove. Now, since x1 and x2 belongs to the inverse image of K, this means that T of x1 belongs to K and T of x2 belongs to K. Right? x1 and x2 belong to the inverse image means that their image are in K. Now, since K is convex, by assumption, this means that alpha Tx1 plus 1 minus alpha Tx2 belongs to K. And by linearity, this is equal to T of alpha x1 plus 1 minus alpha x2. So we just proved that the image of alpha x1 plus 1 minus alpha x2 belongs to K. So this means that alpha x1 plus 1 minus alpha x2 belongs to the inverse image of K, T minus 1K, which is exactly what we wanted to prove, and therefore we proved the claim. So we finish this lecture by discussing Convex Hull. So let me define what a convex hull is. Let's take S a subset of X, not necessarily convex. And now I'm considering K of theta all convex sets and which contain S. Okay. So there is at least one convex set which contains S, which is X. X is a linear set, so it's convex and it contains X. So I'm taking this family, which can be a huge family of sets, all convex sets which contain S, and I'm taking the intersection over all these sets, and I'm calling that the convex hull of S. So this is the definition of the convex hull of a set S. I know by a property already proved that this is a convex set. So the convex hull of S, it's a convex set. Okay? And what I claim is that the convex hull of S is the smallest convex set which contains S. So what I mean by that is that the convex hull of S, it's convex. Okay, because I'm saying it's convex. It contains S. And finally, what I want to prove is that if K is a convex set and K contains S, then K contains the convex hull of S. Okay, so this is what I want to prove. Q of S, it's convex, it contains S, and that if K is a convex set which contains S, then it contains the convex hull. And the proof is very similar to the one in which we proved that the linear span, it's that we characterize the linear span as the smallest linear subset which contains S. So let's prove that it's convex. Well, we already proved it, right? We know that k theta are convex sets for all theta. Therefore, the intersection we've seen it's a convex set. So we already proved that the convex hull is convex. That it contains S, it's very easy because each of these sets, k theta, contains S. Therefore, the intersection contains S. So we also know that convex hull contains S. And now if you consider convex set, which contains S, well, it's one of these elements, because here I'm taking the intersection over all convex sets which contain S. So if K is a convex set which contains S, it's one of these sets on which I'm taking the intersection. And since I'm taking the intersection, K, it's larger than this intersection, which is the convex hull. So K contains the convex hull. So this proves my proposition, which states that the convex hull is actually the smallest convex set which contains S. So now the last property of this lecture is the following. I want to show that the convex hull of a set S is actually equal to the set of the convex combinations of elements of S. So this is formed by all sums from 1 to n of alpha j, xj, such that xj it's an element of S, alpha j belongs to 0, 1, but the sum of the alpha j's it's equal to 1, and n it's larger than 1. Right? So remember, I'm fixing a set S, I define the convex hull. Now I want to show that the convex hull, that we have an explicit expression for the elements of the convex hull, which is very nice. As I said before, for the linear span, the convex hull it's in principle a very abstract space, since it is defined as the intersection of all convex sets which contain S, but it has its elements and have very simple expressions because they are given by convex combinations of elements of S. So we want to prove this identity. So let me call this set the set Z. And what I want to show is that Z is the convex hull. In order to prove that, I'll first show that Z it's a convex set, and that Z contains S. If Z is a convex set which contains S, we know that Z contains the convex hull of S. Okay. So let's prove that Z is a convex set. That's very easy. So let's take an element Z1 and an element Z2 in Z, alpha in 0, 1, and let's show that alpha Z1 plus 1 minus alpha Z2 belongs to Z. Since Z1 it's an element of S, Z1 can be written as alpha j xj, j from 1 to n, and Z2 can be written as k from 1 to m of beta k, yk, where yk is in S, the sum of beta k is 1, xj is in S, and the sum of alpha j is 1. Okay, now let's take the convex combination of alpha Z1 plus 1 minus alpha Z2. Well, this is equal to the sum of alpha j xj plus 1 minus alpha beta k yk. These elements are elements of S. Alpha j is non-negative. 1 minus alpha beta k is non-negative. The sum of alpha j plus 1 minus alpha beta k is 1. It's clear. And therefore, this is an element of the convex combinations of S, which means that it's an element of Z. So we proved that alpha Z1 plus 1 minus alpha Z2 is an element of Z. And therefore, Z is a convex set, right? So we just proved that Z is a convex set. And the fact that Z contains S, it's clear. You take any element of S can be written as 1 times this element, and therefore it's clear that Z contains S. So that we proved that Z contains the convex hull because the convex hull is the smallest among all convex sets which contain S. So now we have to show that Z is the smallest So let's take K a convex set which contains S, and we have to prove that K contains Z. Right? So let's consider a convex set which contains S. Well, since K contains S, we have seen that it has to contain, and it's convex, it has to contain all convex combinations of elements of S. But Z is formed exactly by the convex combinations of elements of S. Therefore, K has to contain Z. And this proves that, Z is the smallest among all convex sets which contain S. And therefore, this proves that Z is indeed equal to the convex hull of S. And this concludes this lecture.